The Dance of the Planets. Let's continue with Zoran the Dragon narrating the Dance of the Planets, learning about orbits, rotations, and the mathematics of planetary movements underscore. Welcome back, my fellow travelers of the cosmos. Today, we'll witness one of the most graceful performances in the universe, the Dance of the Planets. Every planet, including Earth, moves in a beautiful, predictable pattern through space. This cosmic dance has been going on for billions of years, and it's all governed by mathematics and the invisible forces of nature. So, buckle up as we learn about orbits, rotations, and the fascinating math that keeps everything in motion. The circle of life, planetary orbits. First, let's start by looking at the orbits of the planets around the Sun. You may think that the planets move in perfect circles, but that's not quite right. Thanks to a mathematician and astronomer named Johannes Kepler, we now know that planets actually move in ellipses, stretched out circles, rather than perfect circles. Kepler discovered this after years of studying the movements of Mars. He formulated 3 laws to describe how planets orbit the Sun, which are now known as Kepler's laws of planetary motion. These laws revealed that the speed of a planet changes as it orbits the Sun. It moves faster when it's closer to the Sun and slower when it's farther away. This discovery was crucial in understanding that the universe is not as simple as we once thought, but it's even more beautiful and complex. Kepler's first law tells us that the orbit of a planet is an ellipse, with the Sun at one of the 2 foci. This means that planets don't just spin around randomly, they follow a precise mathematical path. The role of gravity, Newton's contribution. Now, let's talk about gravity, the force behind this cosmic dance. Gravity pulls objects toward each other, and it's what keeps the planets in orbit around the Sun. Isaac Newton, a brilliant mathematician, explained how gravity works in his famous book, Philosophiae Naturalis Principia Mathematica, or simply the Principia. Newton's insight was that every object in the universe, from tiny grains of dust to massive stars, exerts a gravitational pull on every other object. This pull is stronger if the objects are closer together and weaker as they are farther apart. The math behind this is described in Newton's law of universal gravitation, which tells us that the gravitational force between 2 objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. This law is why planets don't just fly off into space, they're held in place by the Sun's gravity. But because the planets are also moving forward, their path becomes an orbit, like a continuous dance around the Sun. Why do planets rotate? As we glide between the planets, you'll notice something else: each one spins on its own axis. This is called rotation, and it's what causes day and night on Earth. Every planet in the solar system rotates, but not all of them rotate in the same way. For example, Earth takes about 24 hours to complete one rotation, giving us a day. Jupiter, the largest planet, spins much faster. It takes only about 10 hours to complete a full rotation. On the other hand, Venus rotates so slowly that a day on Venus lasts longer than a Venusian year. And what's more, Venus rotates in the opposite direction of most planets, a phenomenon called retrograde rotation. But why do planets rotate in the first place? It all comes down to the conservation of angular momentum. When the planets were forming from spinning clouds of gas and dust, the particles within those clouds naturally began to rotate. As they clumped together to form planets, they kept spinning much like an ice skater spinning faster as they pull their arms inward. This rotation continues today. Billions of years later, orbital resonance, a gravitational symphony. Let's move on to one of the most fascinating aspects of planetary motion, orbital resonance. This occurs when 2 or more orbiting bodies exert a regular, periodic gravitational influence on each other. For example, in our solar system, the moons of Jupiter Io, Europa, and Ganymede are in such a resonance. For every orbit Ganymede completes, Europa completes 2 orbits, and Io completes 4. This resonance keeps their orbits stable, almost like a choreographed dance. Orbital resonance also helps explain why there's a gap in the asteroid belt between Mars and Jupiter. The gravity of Jupiter has prevented asteroids from forming a planet in this region by disrupting their orbits with resonances, the ellipses and eccentricities of orbits. Not all orbits are the same. Some are more circular, while others are highly elliptical. The shape of a planet's orbit depends on its eccentricity, of how much an orbit deviates from a perfect circle. For example, Earth's orbit has a very low eccentricity, making it almost circular, but Pluto's orbit is much more eccentric, meaning it's more stretched out. A planet's orbit can change over time due to gravitational interactions with other planets. These changes can lead to periods of greater or lesser eccentricity, which can affect the planet's climate. For example, changes in Earth's orbit over thousands of years have been linked to ice ages. Kepler's second law, the speed of planets. Now, let me show you something truly magical about how planets move through their orbits. Have you ever wondered why planets move faster when they are closer to the Sun and slower when they are farther away? This is because of Kepler's second law, also known as the law of equal areas. It states that a line connecting a planet to the Sun sweeps out equal areas in equal times. This means that when a planet is near the Sun at perihelion, it moves much faster, and when it's farther away at aphelion, it moves slower. Imagine it as if the planets are dancing in a ballroom, speeding up as they come closer to the Sun and slowing down as they gracefully glide away. The harmony of the spheres, Kepler's third law. As we soar through the solar system, let's take one final look at Kepler's work. His third law gives us the relationship between the distance of a planet from the Sun and the time it takes to complete an orbit. The farther a planet is from the Sun, the longer its orbit takes. This law can be written as PA equals RA, where P is the orbital period of the planet, the time it takes to complete one orbit around the Sun, measured in Earth years. A is the semi-major axis of the orbit, the average distance from the planet to the Sun, measured in astronomical units. This elegant formula highlights the harmony in the solar system, showing that planets further from the Sun take longer to complete their orbits. This simple mathematical relationship is why Mercury, the closest planet to the Sun, orbits in just 88 days, while Neptune, the farthest, takes 165 years. Conclusion: the cosmic dance. As we return to Earth after this cosmic journey, remember that the movements of the planets are not random, they are governed by the laws of physics and mathematics. Every orbit, every rotation, every resonance is part of a vast, harmonious dance that has been going on for billions of years. With these discoveries, humanity began to understand the universe in ways never thought possible. From Kepler's laws to Newton's gravity, we've seen how math governs not just the planets, but the entire cosmos. So next time you look up at the night sky, know that you're watching a grand performance, one that's been rehearsed for eons and follows the most beautiful mathematical rules. Through the eyes of Zoran the Dragon, we've seen how planets dance around the Sun, bound by the invisible threads of gravity and the eternal music of mathematics. This chapter brings together the wonders of planetary motion with the precise facts of celestial mechanics, grounded in truth, but told with a sense of magic.